Okay, so yeah, initially I forgot that I was doing a tutorial. I thought I was doing a research talk, so you might have seen a title, an abstract related to privacy and private algorithms, differential privacy. But given that it's a tutorial, a 2.5-hour tutorial, I decided to instead do streaming algorithms. So just a show of hands, who here is, let's say, does not identify as a computer scientist, is not a computer scientist? Okay, I just wanted a sense, who here has, has not started a PhD yet? Okay, so good, so okay. So I just wanted to calibrate, I guess, where people are. So what is a streaming algorithm? Basically, you have some large amount of data. Let's say, coming at you. And you want to process it on the fly as it comes, and then answer queries about it later. And the main thing is that we want to design algorithms that use memory sublinear in the data size. So your algorithm should not remember the vast majority of data that it saw. So for example, maybe you have n data points. We're going to be targeting memory that's like log n or log squared, polylog n, things like that. You can think that, again, some of you are not computer scientists, but analogy is basically streaming algorithm is the same thing as low memory dynamic data structures. It's just a fancy way of saying the same thing, right? So for people who aren't familiar with the jargon, a data structure is just a way of organizing data in memory so that you can query it later. And a dynamic data structure means the data is allowed to change. So you're allowed to insert data, delete data, change data. And we want a data structure that uses low sublinear memory, so it actually doesn't remember most of the database. Okay, so like red-black trees and so forth, those things, heaps, all those things are data structures, yes? So I want data structures that don't remember most of the data. Okay, so that's basically what a streaming algorithm is. Okay. I mean, there are other use cases for streaming. Maybe I'm not going to get into all the details, but these things are quite heavily used in industry even today. A lot of the big companies, Google, AT&T, so forth, are using, like telecommunications companies use streaming algorithms. And the idea is, even in cases where you do have enough memory to store the database, if you have a very small memory footprint, then your data structure can fit in, say, cache, so it's even faster, for example. And there are a lot of situations where you don't just store one kind of data structure or one streaming algorithm's memory footprint, but you're running many of these algorithms in parallel, right? So each one is low memory, but in aggregate, there's a lot of memory. So anyway, you want each one to be small so they all fit. They're also useful in some communication settings where one server has, you shard the data out to many different servers. One server is processing some of the data, another server is processing some other subset of the data, and so forth. And many of these streaming algorithms or these data structures are mergeable, meaning if I have a data structure for, data set S1 and I have another data structure for S2, I can merge the data structures later to get one for the union of them, right? So it helps for kind of parallel processing of massive data sets as well. Good. So today, I want to just cover maybe a few kind of foundational problems and results in the area. So one is going to be kind of counting problems. So one is going to be distinct counting. So my data is a set of items from a finite universe. Let's say IP addresses. I'm a router. I see packets being sent. I see source IP addresses for each packet. How many distinct senders sent over this wire over the last hour? So, right, how many distinct, just abstractly, how many distinct elements did I see in the data stream? Okay. Another one is not distinct counting, but just counting. Okay, so this sounds like a very simple problem. Maintain a counter. That's it. Initially it's 0. Increment, 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 increment. n times, what's the value of the counter? That's the whole problem. Okay, so naively, you would use log n bits to store a counter that gets as big as n. So we're going to see how you can actually do it in log n bits. Okay, and then we're going to look at also, lower bounds, what the techniques look like for lower bounds, and we're also going to look at basically finding frequent items. So, so-called top K. On Google, people are searching for things. What's the most frequent word? What's the most frequent topic people have searched for today? What are the top 10 most frequent things people search for today? And then if we have time, I'll show that, I'll talk about quantiles, including some recent works. So here, for both of these, I'll talk about, well, all of these, I'll talk about some recent works as well. Quantiles as well, and also graphs. And some of these are related. So what does quantiles mean? My stream is the following. I'm running some kind of system, and people are issuing queries to the system. And they issue a query, they get a response. What's the latency of that response? It's a number. Right? So there are lots of queries, lots of responses. Each one has its own associated latency. Those latencies are my items in my stream. And then I want to understand what's the median latency, what's the 99.9th percentile latency, and so forth. So quantiles over this data set. That's quantiles. Maybe I'm also looking at quantiles where I can insert and delete items from the database as well. So fully dynamic quantiles. And graphs, maybe I'll just say one thing about graphs. Consider the following problem. I tell you there are n vertices. Initially, the graph is empty. And the stream is Facebook, okay? So people are making new friends on Facebook, and edge got added. Two people got into a fight, or a boyfriend and girlfriend broke up, and then someone defriends someone, the edge got deleted. And then I ask you, find me a path from S to T. Give me a spanning forest of the graph. So naively, let's say maintaining a spanning forest, okay, or let's say maintaining a spanning forest. If there are no deletions in the graph, I can only insert edges. I can do this in n log n bits of space, right? Just basically maintain a spanning forest whenever I see an edge insertion. If those two endpoints are already in the same connected component, I can ignore the edge. If they're not in the same connected component, I'll store the edge. At any point in time, I'm storing a spanning forest, which has at most n-1 edges. So n log n bits to store it. How do you do that, though, when people break up and edges get deleted in Facebook or something, right? I can't just store a spanning forest because maybe, I have my spanning forest I'm storing, a new edge came. I say, oh, I don't need that edge because those two are already in the same component. I'll just ignore it. But then later, someone breaks up, and then the edge gets removed. And all of a sudden, I needed that edge that I had ignored because it keeps the component together. But I don't remember because I didn't keep that edge, right? So it's not clear how you would actually do this in non-trivial memory. The naive thing would be store the entire graph, which could have n squared edges. I would use n squared space. Okay. It turns out you can use n times log cubed n space. So still n polylog n space. And it turns out also that this is tight, that there is no algorithm that uses less than n log cubed n space to maintain a spanning forest. Okay, so we'll see if I have time to actually get to that one, because I only have 2.5 hours and I have 5 things here, so we'll see. So let's start with distinct counting. Okay. Maybe just a show of hands, like who in the audience has seen kind of solutions to at least one of these 5? And who has not? Oh, okay, so vast majority have not. Okay, good. So so input is, let's say, a stream x1, x2, m is the length of the stream, and each one of these items is in some bounded universe of size. Let's call this n. of size u, integers from 1 to u. Okay, and the output is the number of distinct, or basically look at the set of all xi and look at the size. Okay, and just like what is the number of distinct elements in the stream? So example 1, 1, 5, 1, 3. The answer would be 3 because there's, this is the first time I've seen 1. I've already seen 1 before. First time I've seen 5. First time I've seen 3. I've only seen 3 distinct elements in the stream. I should say 3. Okay, so actually our goal is like say that T is the answer. I'm going to output an estimator. I'm going to have a randomized algorithm that's going to provide an estimate of T that's good with good probability. So output T hat such that the probability that T minus T hat is bigger than epsilon T is at most delta. So epsilon and delta will be parameters given to the algorithm. And this probability is taken over the random decisions made by the algorithm. It's a randomized algorithm. Right? So think of epsilon as, let's say, 0.01. That means I'm within 1%. My output should be within 1% of the true answer with probability at least 1 minus delta. Okay. So I guess I'll go over there. So maybe I can actually write right here. Any questions at this point? I get to set delta, but I mean, just think of it. So at the end of the day, our memory is going to depend logarithmically on 1 over delta. So, even if you set delta to be like 1 over 2 to the 100, log 1 over delta is only 100, right? So your payment in your memory for getting very tiny delta is not that high. And actually, when we get to counting, you're going to see that our memory is going to be depend on log 1 over delta. So double logarithmic, and you would well, okay. So 2 ways to think about it. One is ahead of time, you tell me epsilon and you tell me delta, and I'll configure the algorithm will have some parameters. So I'll set the parameters of my algorithm to ensure that I get this epsilon delta guarantee. And of course, if I make delta small, if I make epsilon small, the memory requirements will go up. Or you could also look at it as ahead of time, I give you the memory budget. Like I'm willing to give you 10 kilobytes or whatever, and like what's the best epsilon delta trade-off you can give me with that budget? So, any other questions? So first, I'm going to give you like an idealized algorithm. Okay, who has never heard of hash functions? Never heard of hash functions, ever. Okay, so a hash function for me today is just a random function. So I'm going to pick a random function that maps the set of integers from 1 to u into the continuous interval from 0 to 1. Okay. And then 2, I'm going to store only a single value in my memory. X is the min over all I in the stream. So my stream is x1, x2, all the xi's. The min of h of xi. Okay, so that's it. That's what my algorithm stores, only a single number. And then now, if someone asks me, what is the number of distinct elements? What do I say? Well, if you think about it, let's just draw a picture. Here's 0, here's 1. If I only had 1 element in the stream, where do you expect its hash value to be? You expect it to be a half. In general, if you have t distinct elements in the stream, what do you expect kind of the picture to look like? You expect those t hash values to be like evenly spaced in the interval from 0 to 1, which means they're going to be at like 1 over t plus 1, 2 over t plus 1, all the way up to like t over t plus 1, right? And if I'm storing the minimum, then I'm storing this value. So I'm going to output 1 over x minus 1. Okay? I mean, we can just, maybe I'll just, I don't want to spend too much time doing calculations because there's so much to cover, but these are exercises you can do on your own. So claim is that, the expectation of x is indeed 1 over t plus 1, right? Why is that? Proof. The expectation of x is the integral from 0 to infinity of the probability that x is bigger than lambda d lambda. Okay. What is the probability that the min hash value is bigger than lambda? Well, there's my interval from 0 to 1. For one hash value to be bigger than lambda, it's 1 minus lambda, right? Because lambda it's less than lambda, 1 minus lambda is bigger than lambda, and there are t of them. So it's 1 minus lambda to the t. So this is the integral from 0 to 1 of 1 minus lambda to the t d lambda, which you can calculate as 1 over t plus 1. Okay, so it's nothing too fancy. Okay. Now, okay, so I mean that all sounds reasonable, but it's not going to get me 1% error with 99% probability. Like there's variance there. In fact, you can calculate the variance. So claim is expectation of x squared. So if I want the variance, I want expectation of x squared minus that squared. That's something like 2 over t plus 1, t plus 2, or something like that. And how do you prove that? You just do it again. Expectation of x squared is equal to the integral of probability that x squared is bigger than lambda d lambda, which is equal to, well, that means x is bigger than root lambda. So this is the integral from 0 to 1 of 1 minus root lambda d lambda to the t. And you can do a u substitution or whatever. I think this comes out to 2 times the integral from 0 to 1 of u to the t times 1 minus u du. And you get what I promised you if you just do it, calculate it. And this all implies that, well, variance of x is going to be equal to 1 over 2 over t plus 1, t plus 2 minus 1 over t plus 1 squared. Okay, and if you calculate this, I think you get something like t over t plus 1 squared t plus 2, which is less than 1 over t plus 1 squared. Okay, so the variance is like roughly the square of the expectation, or it's less than the square of the expectation if you do the calculation. Okay, anyway, it's clearly something is wrong because nothing here has epsilon in it. What's the parameter? Like, if at the end of the day I want this epsilon delta guarantee, somewhere in my algorithm there has to be an epsilon and a delta being set. Okay, so how do I get that to happen? Well, I mean, this is kind of a standard idea that people use again and again in streaming algorithms. Which is kind of to take, better, reduce variance by averaging. So what do I mean by that? This is an algorithm. Let's call this algorithm like algorithm 1. Okay. So what I'm going to do is run algorithm 1. Well, let's say, actually, let me slightly change my box. Only the first 2 steps of my box are algorithm 1. So, okay, so it's like, what do I store? So run algorithm 1 like t times in parallel. I'm already using t. R times in parallel. with independent randomness to get, x1 up to xr. Okay. And then what I'll do is I'll set, x average to be 1 over r times the sum I goes from 1 to r of xi. So I average them together. Let's say this is my step 1, this is my step 2, and this is my step 3. And then I'll output 1 over x bar minus 1. Okay. So this is my new algorithm. So before my memory was like one number, now my memory is r. So I blew up my memory by a factor of r. But what can I say about x bar? Just by linearity of expectation, it has the same expectation as x, which was 1 over t plus 1. But its variance got smaller by a factor of r. So I decreased the variance. And let me not, you can use, anyone here not ever seen Chebyshev's inequality? Everyone's seen, who's seen Chebyshev's inequality? Okay, good, okay. So just using Chebyshev's inequality, basically claim, I get the, let's say epsilon eta guarantee, so not delta, we'll get to delta in a second. I get the epsilon eta guarantee, so think of delta as being eta now. With r being up to a constant 1 over epsilon squared eta. And the proof is just Chebyshev's inequality. Okay, so I'm not done yet. This is algorithm 2. Now the output will be part of the box. Okay. Sorry?
This is guiding.
It gives you that your output will be within epsilon of the truth multiplicatively, 1 plus epsilon, and your failure probability will be eta. So this is delta, but I'm getting eta here because I'm going to do something else to get my delta in a second. So I'll call this algorithm 2. Oh, I can't write. I'm not supposed to write there. This is my algorithm 2. Okay, it's visible. Okay. Okay, now and it works. I could just set eta to be delta, and then my memory would be 1 over epsilon squared times 1 over delta. But I forgot who asked the question earlier. How do I set delta? And I said, oh, you can set delta to be super tiny, and you don't pay much. You pay log 1 over delta. This is not paying log 1 over delta. This is paying 1 over delta. So if you want really low failure probability, delta is 1 over 2 to the 100. Then this is not really, it doesn't make sense anymore. Okay, so what do you do if you want, really good failure probability? So even better, is, so run algorithm 2 S times in parallel, each with eta being a third. Not this time. Obtain estimates T1 hat, T2 hat, T S hat, right? Each one of my algorithm 2s gives me an estimator from step 3. And then I'm going to output and I'm going to set S to be some constant times log 1 over delta. And I'm going to output the median of these. This is algorithm 3. Is it clear what the algorithm is? And I'm not going to write it down, I'll just say it. So the point is, there are these S different copies that are independent. Each one has a third probability of failing, right? So in expectation, how many of them fail? S over 3. Okay. Now, basically, you can think I have an indicator random variable for whether or not the jth copy fails or succeeds. Or let's say the indicator random variable is 1 if it fails. And I look at the sum of these indicator random variables. They're independent. Their expectation of the sum is S over 3. For the median to fail, more than half of the copies have to fail, but only a third fail. So for more than half to fail, this sum of these indicators has to deviate from the expectation by at least S over 6 to go from S over 3 to S over 2. What's the probability that that happens? By a turn-off bound, it's like exponentially small in S. So because I set S to be log 1 over delta, exponentially small in S is delta. So that's it. Okay. So at the end of the day, what's my memory? My memory is like basically log 1 over delta divided by epsilon squared. Okay. Now, this algorithm is idealized. Notice I said idealized. It's idealized for 2 reasons. One of them is, computers can't store real numbers. They store bits. That's okay. I'll just discretize this to some small enough precision. You can analyze that. It's not a big deal. The other thing that's more serious is I need a random function, right? So remember my stream 11531. So I first calculate h of 1. I get a number. Later in the stream, I see 1 again. H of 1 had better give me the same number again. How do I do that? Well, I basically need to store the evaluation table of H. But H has a domain of size U. So storing the evaluation table of H would take U memory. There's already a trivial algorithm for this problem using U memory. Just store a bit array of length U and just keep track of what you saw. Okay, so I can't actually afford to store such an H. Who here, I guess, has seen pseudorandomness? K-wise independent hash functions. Okay, so maybe I'll just say a word about that. So the idea is that I'm not going to use a truly random H because I can't afford it. I'll use a pseudo-random H, which is like good enough for my algorithm to work. So let's say K-wise independent hash family, independence. So definition. A collection, a set of functions mapping some domain to some range is K-wise independent if for all x1 not equal to, let me actually not say, yeah, for all x1 not equal to x2 not equal to xk, and also for all y1 up to yk, these are in R, these are in U. The probability that h of xi equals yi, h of x1 had better equal y1, h of x2 has to equal y2. Like, what should this be? It should be 1 over r to the k. If the function was truly random, it'd be 1 over r to the k. But I'm not going to pick h to be a truly random function. I'm going to pick it as a uniform element of script h. So if script h has this property, then I will say that it is a k-wise independent family. It is a k-wise independent set of functions. It's a k-wise independent hash family. That's usually what people call it. And the point is, okay, so what's an example of a k-wise independent hash family? let script H be the set of all functions. The set of all functions that map U to R. Okay. So if you pick a random element from the set of all functions, that is a uniformly random function. How many bits of memory does it take to store little h? Logarithm of the size of the set it came from. How many functions are there? R to the U, right? So basically U log R bits. I mean, that's just saying like, I need to remember h of x1. I need to remember h of 1, h of 2, h of 3. I need to write down the evaluation table. It takes U log R bits. That's trivial, okay? The key is that there actually exist k-wise independent hash families. So claim there exists k-wise independent, like let's say, okay, say, I don't know, U and R are prime. Actually, let's say that, okay, actually, let me, I'll give it even, you know, U equals R is prime. It's a prime number, prime integer. Then there exists a k-wise independent family with the size of H being O of, I guess, let's say, the size of U. So okay, before here I said it was what? What did I say it was? It was R to the U, right? So instead of R to the U, I'll say that it's R to the O of K. Okay, so I mean, if U is R, then over there it was like R to the R. Here it's R to the K. So think of K as 2. In fact, for our situation, we're going to want K to be 2. You'll see in a second. So it's going to be R squared, which means a random hash function doesn't take U log R bits. It takes log R bits. 2 log R, so O of log R. So it's exponentially less memory. So you can actually just store, and the proof is, can let H be basically the set of all degree k minus 1 polynomials over f cubed. So if I have a polynomial p, then h of hp of x is equal to p of x, mod r. Yeah, then you don't gain anything. So you need to show that your algorithm still works even if k is small. Yeah, and maybe, okay, so I'm not gonna prove. Maybe you can think about why that is. Okay, but let me just show you kind of why it's useful here. For our problem, which was distinct counting, why is this useful? I'm going to have to change the algorithm to make this kind of work. Okay, so, but it's going to be similar to our previous algorithm. So instead, what I'm going to do is, here's another thing I could do. Instead of just storing the smallest hash value, store the, what's a good number? Store the d smallest hash values. So let's say, let's call those alpha 1, alpha 2, up to like alpha 1, let's say, is at most alpha 2, which is at most alpha 3, which is at most alpha d. These are the d smallest hash values I saw in the stream. Yeah. Q? Oh, over FR. Yeah, R is a prime. Yeah, so I guess the point here is if I ask, if I have k different hash values and I ask, what is the probability, right? The probability is basically the denominator is the size of a capital H, and the numerator is the number of little h's inside capital H that make that happen. Does it make sense? Right? So it's just a counting problem. If I want to ask, what's the probability that a random polynomial makes that happen? It's like, how many polynomials are there that make that happen divided by how many polynomials are there, period. And if I have k different hash, if I want to say h of x1 is y1 and h of x2 is y2 and up to h of xk is yk, how many polynomials are there that make that happen? 1. This is polynomial interpolation. 1 divided by the number of polynomials, and you'll kind of get exactly what I wanted. Right, so again, what do I expect? So first of all, yeah, I mean, kind of what do I expect the dth smallest hash value to be? D over t plus 1. We saw that picture before. So I'll output so d. What did I say? It's d over. I expect alpha d to be d over t plus 1, right? So what I should do is I should take alpha d, 1 over alpha d, multiply that by d, d over alpha d minus 1. Okay. This again is similar to before. It has the right expectation. Okay. But, okay. And then I'm going to set, I'll pick d to be, 100 over epsilon squared. And then it's going to turn out that this works with probability 2/3. It'll give me a 1 plus epsilon approximation with probability 2/3. How do I make that 1 minus delta? I repeat this log 1 over delta times and output the median. Okay. This, though, I claim it works even if the hash function comes from a 2-wise independent family. H will come from a 2-wise family. It won't be a truly random hash function. And how much memory do I need to draw a hash function from a 2-wise family? Well, there are only something like r to the constant number of hash functions. So to name a hash function is log of that. So I'm going to basically use like log u bits. So my hash function will only cost me O of log u bits. Okay. Why do I only need a 2-wise hash function? Why does this algorithm work? It's very similar to the last algorithm, but it's instead of doing before I went from algorithm 1 to algorithm 2 by averaging and from algorithm 2 to algorithm 3 by median. Here I'm not doing algorithm 1 to algorithm 2. I'm just kind of going straight to algorithm 2. I'm going straight to like getting 1 plus epsilon approximation. And why does it work? Intuitively, think of it this way. You have a very large number of items that you're hashing. So you have a very large number of uniform random variables from 0 to 1. You have t of them. You have t independent uniform random variables from 0 to 1. Before, we were just tracking the minimum, right? The minimum has a certain expectation. But like, there's a pretty decent chance that it's half its expectation. Right? Like there's some fluctuation of the minimum. Well, basically only kind of one value has to get screwed up at the bottom, and that'll completely change the min. What's kind of the most robust order statistic? Not the minimum, but what's the most robust? The what? Well, when I say order statistic, like, is it the smallest, is it the second smallest, is it the third smallest? Kind of which one is the most robust? The what? The middle, yeah, the median. The median is kind of the most robust order statistic, right? Kind of a lot of things have to go wrong to really budge the median away from where you expect it to be. So, but the problem is, if I'm using like the dth order statistic, I need to remember the d smallest hash value. So like it costs me a lot of memory to store the median. I can't afford it, basically. It's going to cost me, t over 2 memory or something like that. So I do the best I can, you know, I'll take the 1 over epsilon squared to smallest. I mean, at least it only costs me 1 over epsilon squared memory, right? And it should be more robust than the smallest. How much more robust is it? Okay, so let's try to understand why, how much more robust it is. So let's define an event. E1 is the event that more than D hash values are less than 1 minus epsilon times D over T plus 1. And let's let event E2 is event that less than D hash values are bigger than 1 plus epsilon D over T plus 1. Okay. Let me, you know, just for now, let me just pretend this T plus 1 is not there. Let's make it T, because make my life a little easier to reason about. Let's just for a second pretend T and T plus 1 are the same thing, okay? You can make this all clean if you do it properly. But here's the point. E1 for me is a bad event, and E2 is a bad event. What I'm going to try to show you is that with good probability, neither E1 nor E2 happen. Let's say that E1 doesn't happen and E2 doesn't happen. Then what does that mean? E1 doesn't happen. Let's say greater than or equal to. If E1 doesn't happen, the number of small hash values is less than D. Okay, which means the dth smallest hash value is going to be bigger than this. Right? The dth smallest hash value will be bigger than this. Let's say E2 doesn't happen. Then at least D hash values are bigger than that, which means the dth smallest hash value is less than that. So if neither of these bad events happen, it means the dth smallest hash value is between this and this, which is good. It means that if I invert and do my calculation, things work out. Now, how can I prove that, you know, that E1 is a low probability event? How can I prove that E2 is a low probability event? Let's just do one of them. Both of them are kind of similar. So let's look at E1. Let yi is the let me also say kind of S is, you know, Z1 up to ZT is the set of distinct elements in the string. And then yi is an indicator random variable for the event that h of zi is small, less than 1 minus epsilon d over t. Okay, so the number of small hash values is equal to the sum of yi. I goes from 1 to t. So the expectation of the number of small hash values is this, which by linear expectation is equal to 1 minus epsilon d. Okay, so let me write this as kind of d minus epsilon d. Okay, so far what have I used about? Have I used the fact that h is a fully random hash function? No. Linearity of expectation does not require independence. So that's already a good sign. Okay, so in expectation it's less than d, which is what I want, right? The bad thing is that it's bigger than D. And I'm saying usually in expectation it's less than D. That sounds good. But now I want to say that it's not just less than D in expectation, it's usually less than D with 2/3, with like 90% probability it's less than D. The way I do that is I say, well, the variance of the sum of yi's, if the yi's are pairwise independent, remember now variance sums up, I get kind of variance of the sum is sum of the variances as long as the random variables are pairwise independent. They don't need to be fully independent. And this is why I need k equals 2 over there. I just need 2y's independence. This is going to be equal to the sum of the variances. But yi is a Bernoulli random variable, right? So the variance is at most its expectation. So this is going to be equal to less than the same thing, less than 1 minus epsilon d. In fact, I'll just say it's like less than d. So what do I know now? So typically, the sum of the yi's is going to be equal to its expectation, d minus epsilon d, kind of plus or minus its standard deviation, which is going to be like c root d. So as long as this c root d is much less than epsilon d, then typically this thing is less than d. So I basically want kind of my c root d to be less than epsilon d, which basically means it's enough for d to be theta epsilon squared. Again, this is just Chebyshev's inequality, which is what I did over there, right? So as long as d is theta 1 over epsilon squared, I do get this thing is typically less than d. And I can do a very similar calculation for event E2, and then do a union bound and say typically E1 and E2 both don't happen, and then things work. That's it, okay? So that's all I wanted to say about count distinct. I spent so far 45 minutes, so I have another 45. Okay, good. So, and I was being the most laborious for this one because it's your first streaming algorithm, and then I'll be less laborious for the next few. Any questions about anything here? Yeah. Would Chernoff give a better D? I don't think so. Yeah, here they're not independent, but okay, so Chernoff, usually get like tail bounds that look like e to the minus lambda squared or something, and that assumes full independence. But if you really kind of dig into the proof of, okay, I don't want to go down into the weeds too much, but the fact that the Chernoff bound holds implies that it holds even under pseudo-random hash, even under KY's independence. So the point is, if you have a tail bound, like for all lambda, my tail bound is e to the minus lambda squared, that tail bound implies moment bounds, okay? And similarly, moment bounds imply tail bounds because you can use Markov's inequality on a high moment. So kind of tail bounds for all, like tail bounds that have this like for all lambda, exponential decay or Gaussian decay, tail bounds like that are equivalent to moment bounds. And then once you have moment bounds, you can say, which moment did I need? Like what's the kth moment that I used to get this particular failure probability? Oh, okay, I only need KY's independence because the kth moment is determined by KY's independence. So kind of once you have a tail bound via Chernoff, you automatically can analyze how much independence you need to get a certain failure probability. So that's not a big issue. But here, I mean, I only wanted constant failure probability anyway because I can always amplify it by repetition with the median later. And to get this constant failure probability, I don't need Chernoff. I can just use Chebyshev. You're not going to benefit at all by using it. And I should also say, it's known that this problem requires 1 over epsilon squared memory. So you're not going to beat 1 over epsilon squared. In fact, maybe I'll just write down kind of what is the, so I showed you an algorithm that gets you something. So so the conclusion is that if you map out the precision and storing the hash function, basically O of 1 over epsilon squared log u log 1 over delta bits suffice. Okay? Because you stored the d smallest hash thing, hash values. You repeated log 1 over delta times. And then you need to store things in finite precision. I didn't really go into the details, but that's another log u bits. And then on top of this, you have to store one hash function that's 2 independent. That's only an additive log u bits anyway, so that's kind of dominated by all this stuff. And this was the algorithm that I just presented to you. This particular algorithm is due to Bar Yosef, JRAM, Kumar, not the Kumar in the audience, a different Kumar, Shiva Kumar, and Trevisan. And this was in 2002. And it's known, but I'm not going to show you, that the optimal space is theta of 1 over epsilon squared log 1 over delta plus log u bits. So you can actually get this. The log u doesn't have to multiply. It's a different algorithm. And yeah, I guess the, yeah, anyway, maybe the references. So the upper bound, Daniel Kane, myself, and David Woodruff in 2010. We got it for constant, we got the right thing for constant delta. For small delta, our log 1 over delta also multiplied that, which is wrong. That was fixed by Błaszczyk, I believe in 2018, maybe 19, my memory is off. And then on the lower bound side, I guess, there was like Alon, Matias, and Segedi, I believe, got the log u part. And that was in 96. And then the 1 over epsilon squared log 1 over delta part is due to JRAM and Woodruff, I think. That was in SOTA one year. I don't remember which year, maybe 2010 or 12, one of those. Okay, so I've already spent too much time on one problem. We have five problems, so 4 to go. Actually, I had five bullets, but one of the bullets had 2 sub-bullets. So I had 6. So, okay, so let's just move on. So next problem is approximate counting. Not distinct counting, but approximate counting. So again, store a counter with 3 operations. One is init. Init should set n to 0. 2 is increment, which increments n. And 3 is query, return n. Okay, so this is, I think, a data structure that 1-year-olds implement. Okay, or they learn how to implement. Okay. Who would have thought that the algorithm you learned when you were a year old is not the optimal algorithm? Again, we're going to be randomized and we're going to be approximate. And if you're the kind of straightforward algorithm, of course, takes log n bits. I'm trying to do better. So kind of Morris, I think it was 1978. It was certainly in the 70s. You can get kind of O of log n bits. It's a randomized algorithm where even the memory is a random variable, but like in expectation, the memory is O of log n. And in fact, the memory is O of log n with like very high probability. Like the probability that you use much more than log n is like log n plus k decreases very quickly. Anyone? Okay, so can anyone give me an argument for kind of like why you definitely can't? Okay, maybe it's surprising that you can beat log n. You can. Can anyone like give me an argument like why you cannot beat log n? Or let's even, let me actually, before I say that, let's say I gave you the number n. You know n. You don't have to dynamically maintain it. I give you n, and I say compress it. Compress it to only use log n bits, and then tell that compression to your friend, and they should be able to like recover it up to a factor of 1% or a factor of 2 or something. How would you compress it and only use log n bits? You know the number, but your friend doesn't know the number. So you kind of have to send a message to your friend so your friend can figure out what n was up to a factor of 2. And your message should only use log n bits. Provide the highest bit, which, well, the highest bit is a 1. Yeah. Yeah, exactly. So basically, and provide, so if you were to write the number in binary, provide the length of it, which is also known as log n. So basically, can compress n to log n bits by compress and define that to be like the ceiling, let's say, of log base 2 of n. Right? And this ceiling is where I'm introducing my error. Right? Basically, all you know is the length in binary. But once you know the ceiling of log n, you know two adjacent integers such that the number sits between 2 to the k and 2 to the k plus 1. So you know the answer up to a factor of 2. And log n, of course, writing down log n takes log n bits. Okay. So this lets your friend recover it up to a factor of 2. What if I don't want your friend to recover up to a factor of 2? I want your friend to recover it up to 1 plus epsilon. 1% error. Then what do you do? Give them the first log n bits. That doesn't depend on epsilon. Sorry, what? Yeah, just change the bit. Yeah, good, exactly. So another thing I could do is I could send them not log base 2 of n, but log base 1 plus epsilon of n, and take the ceiling of that. And now what does your friend know? Your friend knows that since they know this number, they know that basically n sits between kind of 1 plus epsilon to the j and 1 plus epsilon to the j minus 1. Kind of they know right? And so that means they know the answer up to a factor of 1 plus epsilon. How many bits is this? So kind of remember your change of base formula, right? Log of 1 plus epsilon of n is equal to log base 2 of n over log base 2 of 1 plus epsilon. And just by kind of Taylor, this is roughly epsilon. And therefore, the amount of memory you need to write this down, the memory you need is log of log base 1 plus epsilon of n. And by this, that's basically log n plus log 1 over epsilon. Right? Okay, so if this were kind of an offline compression problem, you could solve it with memory that's proportional to log n plus log 1 over epsilon. Right? But just by sending this thing. The whole trouble with this problem is that it's not an offline compression problem. It's this n is being dynamically incremented, and you have to accommodate for that. Okay, so everyone agree? So Morris had a solution. So what he said was, we're going to store something in memory which is not n but x. If someone does init, we're just going to set x to 0. If someone says increment, we're going to say with probability 1 over 2 to the x, x gets x plus 1. Else, do nothing. And then if someone says query, what do we do? We output 2 to the x minus 1. Okay. Of course, this is not going to get my epsilon delta, but let's just try to understand what, and then we're going to fix the epsilon delta part. Let's do a little analysis. Let xn be x after n increments. So I denote x after n increments by xn. Claim the expectation of 2 to the xn is n plus 1. This is why I do 2 to the x and I do minus 1 to get rid of the plus 1. Okay, proof. Expectation of 2 to the xn is equal to the sum overall k goes from 0 to infinity of the probability that xn minus 1 is equal to k times the expectation of 2 to the xn, given that xn minus 1 is equal to k. What is this thing? Well, this is equal to 1 over 2 to the k times 2 to the k plus 1 plus 1 minus 1 over 2 to the k times 2 to the k. Okay, and let's just think about it. So, okay, so I don't want to, again, get too bogged down with calculations. We have a lot to do. This is 2 plus 2 to the k minus 1. 2 minus 1 is 1. So I basically get 1 plus 2 to the k. So if I factor, sorry, this whole thing is 1 plus 2 to the k. So 1 times this sum is 1, right? Plus k times this, plus, the sum of this times 2 to the k. So basically, what you get at the end of the day is this is equal to 1 plus the expectation of 2 to the xn minus 1. And then you do induction. This is equal to n minus 1 plus 1, and then it all works out by induction. Okay. So do induction. And then you can, so we get that, and then you can look at the variance of this thing, the variance of 2 to the 2xn. That turns out to be proportional to n squared. And then you could do the usual things we talked about where, you average lots of these to get the variance down, then you take the median and so forth, okay? That's not the right way to go about things, okay? Because, first of all, if you want to get the variance down, you're gonna have to average 1 over epsilon squared copies. So your memory is going to blow up by a factor of 1 over epsilon squared. So you're not going here, we're kind of hoping to get log n plus log 1 over epsilon. If you do this kind of median of the averages stuff, you're going to get log n times 1 over epsilon squared. It's going to be like exponentially worse than epsilon, right? Does it make sense? Yeah. Question about that? Yeah. Yeah, we'll just call rand. We'll just call, flip a coin x times. like with probability 1/2 to the x, I'll increment, right? So I can just flip a coin x times, one like in sequence, flip a coin, flip a coin, flip a coin, do it x times. And then they all have to be heads. But that's fine. Log x is great. I'm storing x anyway. I'm already storing x, so my memory is log x. So using log x memory to implement the random coin flipping is perfectly fine. Does it make sense? Or you look troubled? So okay, just think about it. So what we're basically saying here is that okay, we're storing x in memory, right? 2 to the x is usually n, right? Which means x is usually log n. Which means if we store x in memory, that's log x bits. Log x is log n. So that's fine. That's kind of what I was hoping for. And then to your coin flipping question, yeah, I mean, to do something with probability 1/2 to the x, I need to flip a coin x times, and I need to remember how many times have I flipped it so far. So I need a counter that goes up to x to remember how many times I flipped the coin. But that counter takes log x bits too. So anyway, my memory is proportional to log x, which is great. Yeah, you just need to remember two things. One is a counter, how many bits have I flipped so far, and the other is just a single bit. Has everything I've seen so far been ahead? Because if I ever see a tail, I abort and I do nothing. Okay. Okay, good. So this median of averages thing is like not great. Oh, I took both of the erasers. So we need to do something a little bit smarter if we want to have this log 1/epsilon dependence. And even Morris in the 70s knew that you could be smarter. So here's a better way to kind of get the good epsilon. So smarter way to get small epsilon. And here's the idea. So if I increment with probability 1.0 to the x, so every time I say increment, I increment. This is the usual 1-year-old baby deterministic counter. What can I say? This has low variance. In fact, it has no variance. It has low variance, 0 variance, in fact, but it has high memory, right? The memory is log n bits, not log n. However, if I increment with probability, say 0.5 to the x, which is what we just analyzed, 1/2 to the x, unfortunately, the variance is kind of not great, but the memory is great. So this already kind of suggests something, which is like, well, I can change the base. Why don't I make the base be 0.99? What if I increment with probability 0.99 to the x? You would expect kind of there to be a smooth trade-off between the variance of the estimator and the memory. And maybe I can make things work if I play that kind of game. So what we'll do, increment with probability 1/1 plus a to the x, where a is a parameter. So here a was 0, here a was 1. We'll think of a where a is going to be something small. You can prove that the expectation of 2 to the xn, or not 2 to the xn, 1 plus a to the xn equals an plus 1. So my estimator now will be 1 plus a to the x minus 1, all divided by a. That's kind of my new estimator. You can also prove that the variance of the estimator, 1 plus a to the xn, is going to be proportional to a squared n squared. You can analyze it. I think I'm right. It's either a n squared or it's a squared n squared. I think it's a squared n squared. But anyway, it kind of goes smoothly to 0 as you make a smaller and smaller. Okay? So then what I can do is basically run this with a being, epsilon squared. I think it might be a n squared. With a being something like a is epsilon squared delta. Okay? And then just kind of analyze it with Chebyshev. And can show that the space is typically log n plus log of 1 over a. And since we chose a that way, it's going to be basically log 1 over epsilon plus log 1 over delta. So your final memory will be log n plus log 1 over epsilon, which is what you like, plus log 1 over delta. So that was kind of the state of the art for a while. And then so myself and Huacheng Yu, this was in pods of 2022, showed that the tight answer is log n plus log 1 over epsilon plus log 1 over delta. So we showed both an upper and a lower bound that you can actually exponentially improve on this, on the upper bound. And in fact, it's tight. You can show a lower bound of log 1 over delta. Maybe I won't give the full, it's quite a short paper. Maybe what I'll do is I'll just sketch the upper bound. Okay. And how do we prove it? Basically what we say is, it's the same, okay, we're going to look at the same exact algorithm. We're going to use this estimator being 1 over 1 plus a to the x. We're going to increment with probably 1 over 1 plus a to the x. Our estimator is going to be, again, 1 plus a to the x minus 1 all divided by a. It's just a different, we don't analyze just using Chebyshev, we do something different. So what do we do different? What we say is, I'll just say it, I won't write it. What we say is the following. We say, okay, so initially x is 0, right? And it stays 0 for a certain amount of time, and then eventually you increment. Imagine you have an infinite number of increments. You don't have n increments. You just have an infinite number of increments. And you're just kind of monitoring the evolution of this random variable x over time. So in the beginning, x is 0, and it stays 0 not very long. In fact, it's incremented basically right away. Okay. So let z1 be the number of increments it takes to go from x being 0 to x being 1. Now you're 1 for a while, and eventually you get incremented to 2. Let z2 be the number of increments it takes to go from z1 to z2, to go from x being 1 to x being 2. In general, zt is the number of increments it took you from x being, when x first became t minus 1, how many increments did it take you for it to become t? That's zt. Okay. And so now what I want to understand is basically the prefix sums of the zi's. Look at z1 plus z2 up to plus zk. Okay. And it's gonna kind of look like, remember we had this analysis for the distinct element counter where we looked at kind of what's the sum of these things being less than kind of 1 minus epsilon times what you expect and so forth. So basically what we're going to say is Okay, let me actually just write this down. ZT is the number of increments it takes to go from x equals t minus 1 to x equals t. And what I'm going to look at is, I'm going to look at z1 plus z2 plus z3 plus z4 plus plus, going forever. How many increments are there actually? N, right? There are actually n increments. So I'm kind of incrementing along, and as I'm incrementing along, when I hit n increments, I'm still kind of at some z. I'm at some zt at that point. If I'm at a zt, if t is kind of too small, I'm in trouble because my estimator will give me something that's too small. If I'm at a t that's too big, I'm in trouble again because my estimator is going to give me something too big. So basically, what I want to analyze is like, let's look at kind of that first point. This is kind of zt where if my t that I end up at is kind of here or less, I'm in trouble because my estimate will be a problem. It'll be too small. And let's look at kind of the next threshold where, so like this is a problem. This is a problem also. I'm kind of happy if I'm in here. This is my happy space, okay? If I'm in a zt that's kind of in this range, it means my estimator will give me a 1 plus epsilon approximation. So what I do is I look at this prefix sum. I look at that prefix sum up to that yellow bar. And I also look at this prefix sum up to that yellow bar. Okay. Yeah, for fixed n. So now it's query time. I do my query after there are n increments, and I want to analyze and say like my answer will be close to n with good probability. So I'm going to basically union bound over 2 of x. So the point is, in expectation, in expectation, I do land in my happy space, but I want to say that this happens with good probability. So what I do is I look at this prefix sum, and I say, what's the probability that this prefix sum is bigger than or equal to n? That's atypical. This prefix sum should usually not be bigger than or equal to n. Because if this prefix sum is bigger than or equal to n, I'm not going to get into my happy space. My n is going to be somewhere before this yellow bar, and I'm unhappy. Okay, so what do these zi's look like? These are basically geometric random variables. And each geometric random variable, what's the problem? So every time I increment, it's like I'm flipping some Bernoulli to go to the next level. How long does it take me to go to the next level? It's some geometric random variable. So I'm summing up geometric random variables, each with different parameters, right? What's the probability that the sum of geometric random variables is like much bigger than I expect? So I need a tail bound for a sum of geometric random variables. And similarly, this sum of random variables, this sum of geometric random variables, like it had better be bigger than n. If it's not bigger, if this bottom sum is not bigger than n, it means that when at my point in time, I'm going to end up somewhere over here, which is like I've overshot my happy space. So I need to say look at a sum of geometric random variables. With high probability, it's not too large. And look at this sum of geometric random variables. With high probability, it's not too small. So I need basically concentration for a sum of geometric random variables, and that's it. And so one way to get a concentration for sum of geometric random variables, I'm curious, who's heard of like sub-gamma distributions? Sub-gamma? Okay. Who's heard of sub-Gaussian? Okay. So sub-Gaussian basically means your tail bounds look like e to the minus lambda squared over sigma squared. Okay. Sub-gamma means that your tail bounds look like Bernstein's inequality. E to the minus lambda squared over sigma squared plus e to the minus lambda over k. So you have a mix of sub-exponential. You have a mix of exponential and Gaussian. So one thing, so there's a whole kind of literature on these kinds of tools. So I'll just verbally say it. And so the cleanest way to do this analysis is to say observe the following things. If you sum sub-gamma random variables, you get out a sub-gamma random variable. Actually, let me actually just let me just write one thing. So definition, if I have a random variable z, I'll say psi sub z of lambda is equal to ln of expectation of e to the lambda z. This is the ln of the moment generating function. And definition, z is sigma b sub gamma if for all lambda that's less than 1 over b in absolute value, I have that psi z of lambda is at most, I think, lambda squared sigma squared over 2 1 minus b lambda. I think this is the definition that you'll find in textbooks. Okay, so the first observation is that if z and z prime are independent, lambda sub z plus z prime is lambda z plus lambda z prime. So basically I think this is called a cumulative generating function or something. I forgot. Yeah, something like that. So the point is this psi function is additive. If the random variables are independent, psi sub z plus z prime is equal to psi sub z plus psi sub z prime. Okay. Already that tells you that if you have a bunch of independent sub-gamma random variables, their sum is sub-gamma. The new sigma becomes like the L2s of all the sigma i's, basically square root of sum of sigma I squared. And the new b becomes the max of all the b's or the min of all the b's. I don't know, whatever makes this thing true, okay? So the sum of sub-gammas is sub-gamma, okay? And then sub-gamma, once you have bounds on the MGF, you get tail downs. Sub-gamma basically is the same thing as saying that your tail downs look like Bernstein. Next, what you prove is geometric random variables are sub-gamma. Why? If you have a geometric p random variable, what's the probability that it's bigger than lambda? 1 minus p to the lambda. 1 minus p is at most 1 over e to the minus p. So what's the probability that a geometric random variable is bigger than lambda? It's at most e to the minus p lambda, which looks like exponential decay. Okay? Exponential random variables are also sub-gamma, you can prove. So if you sum up these sub-exponentials, you get a sub-gamma. Anyway, that's how one way to do it. Maybe the cleanest way to do it with standard technology. Okay? If you do that analysis, though, the tail bounds don't quite work unless x is big enough. Basically, x has to be at least 1 over a for the concentration to kick in. Not x, n. The number of increments, sorry. The number of increments has to be at least 1 over a for the concentration to kick in. That has an easy fix, though. If the number of increments is less than 1 over a, you just store it precisely. You just store a counter. That takes log 1 over a bits. Okay, that's it. Okay. So, and that basically will let you choose, instead of this, you're going to end up choosing a to be epsilon squared over log of whatever delta. If you do this kind of analysis based on concentration of sums of geometric random variables. I have what, like 5 minutes? Okay. So we did counting, which was 1 out of the 5. Okay. Oh no, okay, this is a problem. So we have to do 4 more things. One of them is lower bounds. Maybe in the next 5 minutes, I can do a lower bound. Okay. So there are many different tools that streaming algorithms people have developed to get lower bounds. One is like compression arguments. Another one is communication complexity, information complexity. There's some ad hoc arguments out there. Maybe I'll just show you like a compression argument. So lower bound. So let's just look at, for example, distinct count. We showed today that there exists kind of a low memory algorithm, which is randomized and it's approximate. Right? So you could ask, do I need to be randomized and approximate? Can I relax one of these? Can I be deterministic and approximate? Can I be just deterministic and exact? Can I be randomized and exact? And you can show kind of all those things are not possible. You basically can't relax either. You need to be both. So, claim deterministic plus exact is impossible. When I say impossible, I mean it's impossible in low memory. You need basically linear memory. Okay, let me just prove this in words. So why is it impossible? Suppose there exists an algorithm for distinct elements that uses at most S bits of memory. I want to prove to you that S has to be at least U. Suppose there exists an S-bit algorithm. Then we'll show that S basically has to be at least U. Okay, so why is that? If there's a low memory algorithm, I can use it to define a compression scheme as follows. So let's say we have two players, the encoder and the decoder, the compressor and the decompressor, okay? So the encoder gets as input a subset of the universe, okay? Let's call it A. So I'm the encoder, I get an A, which is a subset of 1 to U. I need to compress it such that if I send it to the decoder can look at my encoding and figure out what my A was. Well, this is just kind of now a counting argument. I mean, there are only 2 to the S possible encodings, right? And I need to have a different encoding for every subset. How many subsets are there? 2 to the U. So 2 to the S has to be at least 2 to the U. So S has to be at least U. So what is my encoding? My encoding is, I will take that streaming algorithm that you told me exists, and the stream I feed it will be the elements of my set. I'll just feed the elements of A into the streaming algorithm. And then my encoding will be the memory footprint of the algorithm. So I'll run the algorithm on A, I'll look at its memory, take a picture, and then I'll send that memory to the decoder. And I'll say, here's the memory, go figure out what A was. Okay. How does the decoder figure out what A was? The first thing the decoder will do, remember this is an exact algorithm. The first thing the decoder will do is it'll ask the algorithm, how many distinct elements did you see? I saw 20 distinct elements. Great, I saw 20, okay. Was 1 in the set? How do I know if 1 was in the set? Let me insert a new item in the stream, okay? And then I'll insert 1. And I'll ask it, okay, now what's the number of distinct elements you saw? It's still 20. Oh, so 1 must have already been in the set. Or if it says it's 21, 1 was not in the set. And then I can just iterate over the whole universe and one by one figure out who was in the set and who was not. And I've decoded. Does that make sense? That's it. Okay, so therefore, this is a valid encoding decoding scheme. Therefore, my memory has to be at least U. 2 to the S has to be at least 2 to the U. Okay. Now, what about, let's say deterministic plus approximate? Why is that impossible? Okay, so have people seen error? Who's heard of like error correcting codes? Who's never heard of error correcting codes? Okay, so just now in the argument I presented, the encoder got a subset of the universe, right? So how many possible subsets of the universe are there? 2 to the u. Let's now not look at all subsets of the universe. Let's look at all subsets of the universe that have size, let's say, u over 100, such that no 2 different sets intersect that much. No 2 different sets intersect in more than 10% of their entries. Does that make sense? It turns out that, so this is a collection of subsets. I want a collection of subsets. Each subset has size u over 100. No 2 of them intersect that much. Okay? You can prove that there exists such a collection of size exponential in u. How do you prove such a thing? Pick a random one. Pick a random collection, and then just analyze it, and it'll work with high probability. Okay? So they exist. Okay. Now, I'm the encoder. I get this set of size u over 100. What's my encoding? Same thing. I'll run the algorithm over the set, and then I'll send the memory to the decoder. So now the decoder has the memory, which corresponds to some subset of size u over 100. Okay. I need to figure out which set of size u over 100 from this collection did the encoder have. So let me just look at all the sets in that collection one by one. And I want to know, like, is it this set 1 in the collection? Is it the set 2 in the collection? Okay, let's look at a particular set B. Is it B? Here's what I'll do. I'll insert all the elements of B one by one. Okay, if B is equal to A, what's the new number of, and then I'll ask it, how many distinct elements did you see? If B were equal to A, how many distinct elements are there? What should it say? If B is equal to A, what will the answer to query be? So A had size u over 100. The encoder fed A into the algorithm. It took the memory, and the memory is the encoding. Now the decoder wants to know, is A equal to B? The decoder will feed all of B into the algorithm as well. So it already saw A. Now it's also seeing B. And then it's going to query, how many distinct elements did you see? If A and B are the same, how many distinct elements has it seen? U over 100. If they're different, though, now how many distinct elements has it seen? It's gone up by at least 1 because they're different. It's at least seen 1 new element, right? But actually, it's seen a lot of new elements because what did I say? I said no 2 sets have a large intersection. So kind of the number of distinct elements it's seen has almost doubled, right? It's basically it's like the new thing is like basically A union B, which is the size of A plus the size of B minus the size of the intersection. But the intersection is tiny. So it's almost twice as big. But I have I do have a good approximate algorithm. My algorithm can give me the correct answer up to 1% error. So if I know the answer up to 1% error, I can very easily distinguish the case where it's u over 100 versus roughly 2u over 100. I mean, those are off by a factor of almost 2. So 1% error can distinguish them. So that's it. So basically, I have the memory footprint. I add B in. I query it. Oh, B was not equal to A because the answer blew up too much. So it's not B. Let me reset the memory to the message I got. Let me try a different B. Let me try B prime. Oh, it's not B prime either. So I basically loop over this exponentially sized collection. I try each set in this collection one by one until it tells me an answer that's roughly u over 100. And I'm like, oh, that must have been A. So now what's my memory? Log the size of the collection. But the collection is exponentially big. So that's proportional to u bits. Okay? And so deterministic plus approximate is impossible. How about randomized plus exact? I'll let you think about that. It's a very similar argument to deterministic plus approximate, actually. But that's an exercise for you. You're going to use the same kind of collection of exponentially large collection with small intersections. You can think about how to make that work. Okay, so now we've done 2 things. We've done counting, we've done lower bounds. What did I promise you? I promised you freq 5. So the next one was like frequent items, quantiles, graphs. Okay, so we can take a break, okay.